Welcome to VTish. Now we are going to discuss about acceleration in the slider crank mechanism. So in the previous topics we discussed about the velocity diagrams, acceleration diagrams, velocity in the slider crank mechanism, different links, all those things. So now in this topic we are going to consider acceleration in the slider crank mechanism. So a slider crank mechanism as shown in figure, as you can see here, this is the slider crank mechanism. In the previous also we discussed in so many points. So this is the piston connecting rod, which is the AB link with the angular velocity omega with radius r, which is going to rotate like this. This is the point here. This is the working mechanism of slider crank mechanism. So let the crank OB makes an angle theta with the inner dead center IDC and rotates clockwise direction about the fixed point O with uniform angular velocity omega BO radians per second, as I explained here, which is going to rotate like this with OB link in the clockwise direction. And therefore velocity of B with respect to O, or velocity of B, because O is fixed point, which is going to write it as VBO equal to omega into BO into OB, acting tangentially at B point. So we know that the centripetal or radial acceleration of B with respect to O or acceleration of B, because as we know O point is fixed, so acceleration of BO equal to AB equal to omega square BO into OB, which is going to write as V square BO by OB. Here we need to consider one more point here. A point at the end of the link which moves with a constant angular velocity has no tangential component of acceleration. That is a point we need to remember while drawing the acceleration diagram for the slider crank mechanism. So this is the slider crank mechanism and this is the acceleration diagram. As you can see here, this is the point B and B dash AB dash link. There we are going to have AA and ATBAB, which is going to have two components, centripetal and tangential components. As per the point O here, this is the A and this is the B. So we can write as acceleration of B and acceleration of A, and this is the ATAB and this is the point A here. And this is the AR. There are two components, radial and tangential. So by all these components we are going to get acceleration diagram. So the acceleration diagram as shown in diagram as we discussed now. So draw O dash B dash parallel to BO and set of equal magnitudes BO B AR equal to A to some suitable scale. As we discussed, O dash B dash O dash A dash. From the B dash, draw a vector B dash X parallel to BA. So this is the BA. We are going to draw this one B dash X. By this we are going to get the both tangential and radial components. So the vector B dash X represents the radial component of the acceleration of A with respect to B, whose magnitude is given by ARAB equal to B square AB by BA, as we discussed. Since the point B moves with a constant angular velocity, there will be no tangential component of the acceleration. This point we gave it here, not in the previous while saying this one. Okay. From point X, draw a vector X A dash perpendicular to B dash X. So this is the X A dash. See here, this is X A dash and X B dash. So the vector X A dash represents the tangential component of acceleration of with respect to B, that is alpha ATB. Note, when the point moves along a straight line, it has no centripetal and radial component of the acceleration. This is the point also we need to consider while drawing the acceleration diagram. Since the point A reciprocates along AO, as you can see here, this is the AO, which is going to rotate around the AO. This is the point here. We can write it as here also. Therefore, the acceleration must be parallel to the velocity. Therefore, from O dash, draw O dash A dash parallel to AO. We already drawn it. Intersecting the vector X A dash. See here. So this is the X A dash, and this is the OA dash. Where both of them are intersecting here at this point. Now the acceleration of the piston or a slider A in brackets of AA and AB at may be measured to the scale. Coming to the next point, the vector BA, which is the sum of the vector B dash x and XA dash, represents the total acceleration. As we discussed in the previous one also, this is the total acceleration line A with respect to B, that is alpha AB, sorry AAB. The vector B dash E dash represents the acceleration of the connecting rod AB. Okay, so this is the connecting rod where we are going to get here. This is the AB. From this point, we are going to get the entire acceleration, total acceleration. The acceleration of any point, any other point on AB such as E may be obtained by dividing the vector A dash, B dash at E dash into the same ratio, that is E divides AB. As you can see the diagram here, this is the point which is going to divide the AB line in two parts. By this we are going to get A dash B dash by A dash B dash equal to AE by AB. Similarly, the angular acceleration of the connecting rod AB may be obtained by dividing the tangential component of the acceleration of A with respect to B, which is going to call it as AT here, to the total length AB. In other words, we can call it as angular acceleration of AB. Therefore, alpha AB equal to alpha dash AB, sorry, alpha T, that is going to call it as alpha T. This is the tangential force TAB by AB in clockwise about B direction. So by this we are going to get. So we are going to get the acceleration diagram for this slider crank mechanism. There some examples are there. We are going to continue in the next class. Thank you.